Amateur radio operators usually have to make compromises. Buildings have an influence on the radiation characteristics of a shortwave antenna. Since measurements for this would be extremely complex, we simulate these influences with NEC. Today I'm going to talk about a popular shortwave antenna that a friend of mine operates on the roof of his house. It has a rotor and it is tunable for frequency bands from 40 meters up to 6 meters. It thus covers interesting frequency ranges for worldwide radio connections. The antenna recently smoked and he had to rebuild it. I will link you to the video on the top right corner. That last video gave rise to the idea of analyzing this antenna with NEC, because there are a number of questions that probably other amateur radio operators are asking themselves too. Ham radio operators usually have to make a lot of compromises when positioning an antenna, and then of course there is uncertainty about a number of issues. The immediate questions are around the radiation patterns. Is my building affecting the radiation characteristics? What is the effect of the antenna height? And how are tall buildings in the vicinity influencing the wave propagation? Then there are some further interesting questions. Does the building affect the antenna matching? Is there cross-polarization? If you have similar questions, please let me know in the comments. While NEC is quite a complicated tool, it's very powerful and free, and I'd like to say a big thank you to the developers. Here are my reasons for using CocoaNEC. The user interface of the geometry and the control for the NEC application is structured like a programming language. I like that very much because it allows you to work very flexible with variables and vectors. This is especially important for this project because I can duplicate the grid models for the houses and transform them to a new location. And that really saves a lot of work. We can also graphically represent the wire grid model very nicely, as you can see. Then there are a couple of ways to display the radiation patterns, which I also really appreciate. Oops, now I accidentally gave away a little bit of the next episode with my little NEC demonstration. Anyway, the numerical results are also available via the user interface. CocoaNEC runs on macOS, and I don't know any better NEC version for the Mac. I would have wished for a near-field calculation and a graphic representation, but you know, you can't always have everything in life. In addition to my results, I also make the native NEC input files available in the download area. With that, you can also run my NEC simulation on any other NEC version that runs on Windows, Linux or whatever. So let's start. First, we need to briefly talk about the two different modes of the antenna. In the 40 meter band, the antenna works as a half-wave dipole with bent ends. As a result, the width of the half-wave dipole is not 20 meters, but only 12 meters. That makes a big difference in the mechanical construction, since the wind load and the resulting forces are significantly smaller. Of course, the curved antenna is not quite as efficient as the straight half-wave dipole. Of course, we will investigate that as well. Incidentally, the reflector and the director are completely retracted in this mode. The two bars make the construction more stable, but have no influence on the radiation properties of the antenna. In the 20 meter band, the dipole is shorter in order to match the higher frequency, and both the reflector and the director are effective. The dipole is then a half-wave dipole that is not bent. By the way, you can fine-tune the antenna matching via the length of the director. This works in reality as well as in the simulation that we run. So we now have a 3-element Yagi-Uda antenna where all 3 elements can be tuned separately. Incidentally, the same applies to the higher frequency ranges up to the 6-meter band. In this video we analyze the 40-meter band mode, and in the coming video we analyze the 3-element Yagi mode for the higher frequencies. As already mentioned, we are interested in the influence of the bent arms of our dipole. The radiation pattern of the antenna in free space looks practically the same as the radiation pattern of a half-wave dipole. We see the typical donut characteristics, but the gain is slightly lower. The directivity is 1.88 dB. The gain is only 1.71 dB because the matching is not perfect in the simulation, and there are slight differences in the radiation patterns that we cannot see yet. Compared to the ideal half-wave dipole with 2.15 dB directivity and gain, we lose 0.27 to 0.44 dB. If we convert that into transmission power, then that equals to 6.4 to 10.6% loss compared to the ideal dipole. The truth lies somewhere between these two values. It is remarkable that there is relatively little loss, because the curved antenna is almost half as wide as the half-wave dipole. Interesting, isn't it? Next, we simulate the antenna over real ground. We position the antenna at a height of 15 meters and select average ground for the ground model in NEC. We get a horizontal azimuth plot exactly as you would expect it. It looks almost exactly like the azimuth plot of a half-wave dipole. However, we do get cross-polar components, which I have shown dashed here. These are caused by the fact that we have currents flowing not only horizontal on the antenna, but also vertical ones flowing over the arcs of the antenna. For the elevation diagram, we would like to have a lower beam angle, but that's one of the compromises we have to make. Of course, we are very curious to see what role the antenna height plays. So, let's look at a few different antenna heights. At a height of 5 meters above ground, the antenna would radiate vertically upwards. Of course, that's not what you want at all. Actually, one would like to have the main radiation direction at a low elevation angle in order to achieve the best possible radio range. With an antenna height of 10 meters, the vertical diagram becomes wider, but most of the energy would still be radiated upwards to the sky. An antenna height of 20 meters would be better than 15 meters, since the gain is higher and the main beam direction has a lower elevation angle. A height of 30 meters would be even better in that matter. Okay, we're going back to a 15 meters antenna height. It's just what we have. Now we want to see the impact of our building. Therefore, we model the building as a wire grid model. It is pretty simple, but it corresponds quite well to the electrodynamic properties of a building. The essential conductive structures are taken into account, and at a wavelength of 40 meters, this is quite sufficient to see the effects that interest us. And of course, we can rotate the antenna in our model as we wish. In the azimuth diagram, we can see a slight effect of the building. The whole radiation characteristics becomes asymmetrical. The difference in radiation strength between the two main radiation lobes is about half a dB. And the main beam lobes are both bent by about 5 degrees to the west. The effect is also visible in the elevation diagram. Overall, however, the influence of the building is relatively moderate. I would have thought that we would see stronger effects here. The antenna height of 15 meters, which is about 4 meters above the building, is not 100% ideal for the 40 meter band antenna, but it seems viable anyway. A slightly higher mast would be desirable, but is probably not possible due to the application regulations. And of course, a higher mast would also be significantly more expensive. Now we simulate the antenna rotation, because there could be some influence that depends on the rotation angle relative to the building. I implemented the antenna rotation angle in such a way that you can set any desired value for it using only one variable. In the next simulation, you can see a weak dependency of the impedance and the return loss from the rotation angle, which we can actually perceive also in reality. It's amazing that this dependency is so weak, since the distance to the roof gable is only about 4 meters, which of course is quite small at a wavelength of 40 meters. But I need to mention that we don't have any resonance effects in the structure of the house. It might be interesting to simulate something like this. What do you think about it? Now let's add a few more houses in the vicinity as an example. This increases the computing time, but we want to get a feel for how the surrounding buildings affect our radiation pattern. Of course, we get reflections from the buildings, which then superimpose with the main signal. The radiation patterns are getting ripples from that. We also see very nicely that the radiation pattern becomes slightly frequency dependent as a result. We see variations of 3 dB and more within the 40 meter frequency band. In reality, there are certainly more reflections. We only have the most important buildings in the simulation. And even if the antenna didn't emit any cross-polar components, we would have some at least by now. From the azimuth diagram you can see that the wave propagation is somewhat more restricted towards the north than towards the south. The elevation diagram shows that the main radiation lobe is pushed up in the north direction. That's plausible, given the large buildings in the north. By the way, not only two directions of polarization arise. Circular polarized waves are also generated. Yes, electromagnetic waves are actually a bit more complicated than they are often represented in simplified models. By the way, have you already liked the video yet? The insights. I'm now summarizing the results for the 40 meter band antenna, as we have already produced a lot of results. For the analysis of the antenna in the 20 meter band, I make a second video, otherwise it will be just too much for today. We were actually able to show some interesting effects related to the buildings, the orientation of the antenna, and most importantly the height of the antenna. We always knew that buildings affect the radiation somehow. Now we have quantified it, at least for a typical private house. The curved dipole is losing only 10% antenna gain compared to the half-wave dipole. And that is amazing, considering that it is significantly smaller. The simulations with the buildings in the vicinity gives us an idea that wave propagation is quite volatile, even at this relatively large wavelengths, due to the superimposition of reflections. Overall, however, the obstruction by buildings to radio waves is quite moderate in the 40-meter band. Long radio waves certainly have an advantage here. I'm very curious to see the results of our analysis for the 20-meter band. Maybe the video will help you to better understand the situation in your own case. What do you think? Write me in the comments. Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.